Today, I welcome Tanya. She works at the Research Support Services at the Medical Library, and she will talk about statistical data. Welcome, Tanya.
So have you ever come across one of those dense diagrams in studies, especially in meta-analysis, called forest plots? And did you ever feel like you couldn't see the forest for the trees, as we say in German, den Wald vor lauter Bäumen nicht sehen? So don't worry, today we'll walk through the forest together. So this is a forest plot, and I chose it for today's coffee lecture because it combines several statistical measures in one visualization. Why is this called forest plot? With a bit of imagination, you can see something like a branch, the branches of a tree. So it's even more apparent in the Cochrane logo, and forest plots are typically found in meta-analysis. A meta-analysis systematically summarizes the results of several studies on a research question, thereby increasing the statistical significance of the measured effect. In medicine, meta-analyses help to better assess the benefits or harms of therapies and support evidence-based decisions. If we take a quick look at the evidence pyramid, we see that meta-analyses are at the very top. This indicates that they usually provide high-quality information compared to other study types. So let's get back to the forest plot. In this example, we have the population size, the odds ratio, the confidence interval, and the line of no effect. So let's examine these values so that we can interpret the forest plot. The square represents the population size of each study that was analyzed in the meta-analysis. The larger the square, the larger the population size. The small vertical line going through the square stands for the effect. In our example, we will discuss the odds ratio. However, it could also represent other effects, effect measures as well. So the horizontal line crossing the square shows the extent of the confidence interval. Usually, it's calculated for 95%. And there is also a line of no effect. If the effect or the confidence interval crosses this line of no effect, it means that the effect of the intervention is not statistically significant. And then the red diamond represents the pooled effect, means everything, all the studies pooled together, the effect size of all studies together. And of course, here you have the overall confidence interval. So that is what you find in such a forest plot. Now let's dive first into the population size and its effect. In this example, we have a small cohort study that investigates whether smoking leads to cancer. It includes here only 12 subjects. With such a small sample size, the outcome, I think you agree with me, could be just random. So it doesn't have a lot of value. You may have heard of the law of large numbers. So according to this law, the values of an experiment approach the true value, so the true value of a population, of the whole population, as the sample size increases. So ideally, study the entire population would, of course, yield a true value. However, this is usually not possible, so we work with sample sizes. And this is where the confidence interval comes in. It represents the probability that the true effect in the whole population of smoking, so if all smokers all over the world were studied, lies within this specified range. So in general, the larger the population we study, the narrower the confidence interval becomes. This means that the estimate of the effect is more precise. So in our example, we see that the confidence interval here for the larger exposure group indeed became narrower. So it's here, it's narrower when we draw this gray lines. So regarding this second example, we can conclude now that we are 95% confident that the true proportion of individuals with the effect, means cancer here, in the exposed group, the smokers, lies between 34.9% and 90.1%. That's what I hear. I calculated that. So, but this lecture is about interpreting, so I won't go into that here. So we have still a quite extended confidence interval. So in a sense, this is not very reliable because there's like almost, it's 55% in between. So, but still, this is how it became narrower, even with a larger population. But of course, this population still is very small, usually for real world studies. So in summary, and that's actually the takeaway, because it shows how population and confidence interval are knitted together. So usually the larger the population, so if the population is large, the narrower the confidence interval becomes and the more precise is the estimate of the effect. Conversely, a wide confidence interval indicates greater uncertainty. If the confidence interval is just 0, then smoking has no effect or it is statistically not significant. So there is where the p-value is often used for statistical significance, but today in this lecture we don't have the time to dive into the p-value, so maybe this could be a topic for a next lecture. So now let's look at the effect measure, so our odds ratio, which was the small vertical line in the forest plot. The odds ratio indicates the extent to which an exposure is associated with an event. So this is a prospective core study, and it looks at whether smoking is associated with developing cancer. And actually, we just look here at the outcome groups. Everything here is not interesting for calculating the odds ratio. So we have here the top group, the smokers, and we see 4 people develop cancer, while 2 do not. So the odds of getting cancer in these groups, or the chances, are 4 to 2, which equals 2. So this is this 2. In the bottom group, so the non-smokers, only 2 develop cancer and 4 do not, giving odds of 2 to 4 or 0.5 here. And now with these two odds, we can calculate the odds ratio. So it's 2 divided by 0.5, and we get an odds ratio of 4. This then means that smokers have a 4 times higher chance of developing cancer compared to non-smokers. So you might be confused a bit by this odds ratio and wonder why we don't examine just the relative risk of the 2 groups. Actually, we could, and it's also done in meta-analysis. Relative risk compares the probability of an event in an exposed group and the probability of an event in an unexposed group. So here now we compare the rate of developing cancer with the number of individuals in each group. So we look at these groups and then look what happens when smoking or not smoking. So here you see the risk of developing cancer if you smoke is 4 out of these 6. So these are not interesting, these 2. So it's this 6 and 4 out of them, they develop cancer. And the risk of developing cancer if you don't smoke is here, these 2 out of these 6 people. And then combining these 2 rates, leads us to the relative risk, which is 2. And this means that the relative risk to get cancer is 100% higher if you smoke than if you don't smoke. So because it's like twice, 100%. So why did I show you the odds ratio, even though relative risk is much more intuitive to understand? The reason is that the odds ratio can be applied to all study designs, not unlike relative risk. For example, the relative risk doesn't work in case control studies because, as you've seen in the example, there we just look at the outcome. We just look who has cancer and who doesn't. And then we look back in time to see who smoked and who didn't. But we don't know the actual group size. And that's why we can't calculate the relative risk. So we can only estimate the relative risk via the odds ratio. That's why. But however, relative risk is more accurate when the outcome is rare. And in such cases, the odds ratio again can just approximate the relative risk. So this is just an overview. Back to our forest plot. So here you see now the different odds ratios for the included studies. Some report a negative effect and some have a positive effect. So everything that's on the right-hand side of the line of no effect is a positive effect. And the red line here, it's the overall effect over all studies and it's positive. And it's 1.25, so 25%. So we now went through all the elements of a forest plot and can interpret it now. So the red diamond tells us overall, smokers had a 25% higher, so this is this 25, 1.25, had a 25% higher odds of developing cancer compared to the control group, indicating a statistically significant association because the confidence interval here doesn't cross the line of no effect. And we are 95% confident that the true odds, so if we would know the whole population of cancer in the smoker groups, are between the 10%, so this is here 1.1, so 10% and 40% higher than in the control group. So this is what you can read out of this forest plot and out of this diamond. So I hope this short lecture helped you to recognize the individual trees and thus the forest and the forest plot. I think there is still a little bit of time, so we can look at this overview because meta-analyses don't only work with odds ratios or relative risk. You can even use aggregated data like hazard ratio or mean differences and so on. And it's even possible to analyze studies with more than 2 interventions. This is then called a network meta-analysis. You can also meta-analyze individual patient data that doesn't come out of published study, for example, for subgroups or time factors or other endpoints. And it is called meta-regression if you meta-analyze data like study designs, years, doses of interventions, and so on. So this was a very quick glimpse into the world of aggregated data. If you want to dive deeper into how data informs knowledge and decisions, I recommend you to come back to this website, unib.ch/UB-medresearch in like half a year's time. Then we plan to launch an e-learning platform about data literacy. So there we will go, or we'll talk more and have learning material about data, what it is, and how you can use data for knowledge and decisions. So stay tuned. You can find all the slides and screencast of previous lecture via this link, bip.unib.ch/SciMed, or via the QR code.